Greetings, everyone. Mr. Keister here with you again today. Today, as I look back forward, this is the video for Thursday, August 27th, which is our scheduled 6th day of school for the fall semester. Always keep in mind, though, that the dates could possibly change for a variety of reasons, but regardless of that, the lessons will remain the same. Now, today's lesson actually will be your if you're in Chem 2 or you're if in Honors Chem 1. Today's lesson just so happens to be the same for both classes. That does happen on occasion in some units. If they follow sequentially the same, that will occur more often. But at some point here, Chem 2 students, since you have already had introductory chemistry, I kind of go off in another direction with you guys than I would for students who have not had chemistry at all, which then would involve Honors Chem. But this just so happens to be one of those days where the lesson is the same. And so, like I said, on occasion that will happen. This is the schedule, or the do nows, for Chem 2, all right, which shows that today you will be picking up page 16, Unit 1 Measurements Review. Let me quickly flip to the Do Nows board for Honors Chem because it's very similar. And there it is right there. And as you can see, just here, you actually are picking up two things today. Lab Activity 1.1 Part B, which is page 15, and then the Unit 1 Measurements Review, which is page 16. So slight difference there, but not much. As far as what we did yesterday and what is happening today, again, they're going to just follow each other almost to the letter. So hopefully just make sure that Chem 2, of course, you're referring to yours daily schedule, and Honors Chem, you're referring to yours. So today in class, I just want to quickly mention a quick review of properly recording a rounding and measurement that we went over yesterday in regards to an electronic device as compared to a manual device. I'm going to go over some of the material in your Units 1 note packet, or for Honors Chem, it's Unit 1.1 note packet in regards to matter, and we're just going to get started on measurements today. Homework for tomorrow. This is Honors. In Honors, you will complete Lab Activity 1.1 Part B. This is more practice in regards to recording and rounding and measurement that we went over yesterday. And then you're to work on Unit 1, today's assignment, Unit 1 Measurements Review, today's other assignment, I should say, numbers 1, 2, and 3 only. Now, Chem 2, you only have the Unit 1 Measurements Review, so your assignment for tomorrow is also to be numbers 1, 2, and 3 only. Both classes have a Mastering Chemistry assignment assigned. As I mentioned yesterday, you should already be enrolled in Mastering. You access it through My Lab and Mastering tab on my Canvas homepage. You should already have done that. You already have had the instructions with you now for several days, and you should already be working on your assignments respectively. Hopefully, some of you are even done with them. But either way, either class, that first assignment mastering is due this coming Monday at 7:30 a.m. And again, I am a stickler on mastering dates and times. There is no late extension or anything like that. I set them up for you enough days in advance that I feel that that's enough. So, and that's the way it's going to be in college too, by the way. So it's due Monday morning, 7:30. Whatever you have done at that time is the score you will receive. Okay? If you have any questions on mastering questions, I'll say this one more time because I'm not going to harp on this every single time. If you have any questions regarding mastering, you need to ask me or ask a friend or whatever, but you get like 5 or 6 chances to answer each question. If you haven't answered it correctly by the second or third chance, Something's going wrong. All right, so you need to investigate. You can email me anytime. If we're here in school, you can swing by and see me if I don't have another class, or if it's quick between classes or lunch or whatever. But you need to ask me. There's no point in you not receiving credit for a mastering assignment or problem on an assignment without having the opportunity to see what you're doing wrong. All right, that's what I'm here for. Help you out. And the last thing about mastering is your e-textbook. All right. That is located on your Mastering Chemistry homepage. There's an icon there for the textbook. Just click on that. If you ever want to use the textbook as a reference, it's right there. Okay? Okay. I think we're ready to roll. So let me, I'm going to bring up the notes packet first, but then I want to talk briefly about recording and rounding and measurement that we went over yesterday. So hang on real tight. Page 1 of our notes. So about recording and measurement. All right, so just brief review. We have electronic devices and we have manual devices. The electronic device, the rounding is done for you. All right, however many decimal places your device tells you, that's what you use. All right, you do not vary from that at all. Our electronic balances go out 2 decimal places. That's what you record. Even if you find the mass of something and it says 3.00 grams, that's what you write. You don't write 3. You don't write 3.0. You don't write 3.000. All right? It's 3.00. If you have a number that flips back and forth, that's because of the uncertainty involved. You need to pick one. All right? You don't extend it out another decimal place and say, oh, well, maybe it's halfway in between those two. Don't do that. Just pick one. Okay. For a manual device, right? For a manual device, you have to determine how far to round yourself. That is dependent upon the value of the smallest marking on the measuring device. Remember, you record one place further out than the value of the smallest marking on the device. So if the smallest marking on the device goes to the ones place, then you round to the tenths place or the 1 decimal place. If the smallest marking is the tenths place, then you round your measurement to the hundredths place or 2 decimal places. All right, 1 place further out than the value of the smallest marking. Okay, very, very, very important. Okay, all right. So we've moved on from there, I hope. Okay. So I want to talk about the initial several pages of your notes packet. And for Chem 2, this should be review, all right? And even for those of you in Honors Chem, a lot of this stuff I'm sure you've heard before in your general science classes in upper middle school and whatnot. So, but remember, as I go through the notes packet, and I'll try and mention this more often than not, as I told you maybe at the beginning of the year in my introductory video, I have done these notes packets for your benefit. All right, so years ago, we didn't have these. The teacher or the professor wrote his notes on the chalkboard, and we, the students, frantically wrote out everything he was trying to write down, he or she was trying to write down, which is about impossible. It slows things way down. You miss stuff. It's just got inherent issues with it. So over the course of 25 years, I have created and altered many times through the use of multiple textbooks that I've used over the years, including college ones. Mainly they are college ones. Condensed the notes for a particular unit into these notes packets. So 90% of the notes are written for you. Right? They're written for you. However, you're going to see blank spaces where I'm going to be writing stuff on the board. When I do that, you need to be writing, all right? Or you're missing something. You're missing something. If I'm writing it down, it's important. And if I'm writing it down, in all likelihood, you're going to be tested on it at some point, in some place. So, like I said, 90% of the writing is done for you. So I don't see a real big problem with you writing down the other 10%, as I do it myself on the board. So Just wanted to be clear on that. I'm not going to harp on that. It's up to you whether you're going to write stuff down. You're like, well, I don't need to write that down. I know it. That's fine. That's up to you. But, all I'm saying is maybe that thing you didn't write down is going to be the thing that comes back and bites you later on test and keeps you at a B instead of an A or a C instead of a B. You get what I'm trying to say. In this class, every last point matters. Every last point. You don't want to throw them away needlessly. There's some a lot harder to earn than others. And so the ones that are not hard to learn, you don't need to be throwing those away. It's just not a good idea. All right? Not a good idea. So there's my little speech about that. I don't think I'll harp on that again, so hopefully you won't have to endure that again. Okay, so chemistry. Study of the composition of substances and the changes that they undergo. Almost everything in our lives is affected either directly or indirectly by chemistry. One for advancements in chemistry, we'd all still be living in the Stone Age, and that is the absolute truth. All right? All the things that we use, wear, eat, drink, everything. All the energy that's required today for us to do all the things we do, to have modern conveniences of life, chemistry related, I'm telling you. All right, all of it. So it's relevant. There are 5 main branches of chemistry: organic, which is the study of most compounds that contain carbon. Organics, and we're going to spend a unit on organic chemistry in here later on in both classes. And so more specifically, organic chemistry, while the compound must contain carbon, it also must contain hydrogen. All right, carbon-hydrogen bonds. That's what distinctly defines organic. Inorganic, the study of all other substances that aren't classified as organic. Analytical, the study of the composition of substances. We'll be doing a lot of that. Biochem, the study of the substances and processes of living things. I make a lot of references to biochem throughout this course or these courses, but we don't really tend to focus on biochem specifically. But I certainly make a lot of references to it because a lot of biochemical processes that occur within our bodies or within plants or other animals or whatever, certainly directly related to chemistry. And then physical chemistry, the quantitative approach to the study of all types of chemical problems. Man, that's where it's at. Like I said, in chemistry, we record a lot of numerical data, and then we take that data and manipulate it in a multitude of ways to get answers to things. All right, and so we are going to do a lot of that throughout the year. Okay, advance here. Scientific method. I know you guys know this. You've been working with this probably since elementary school. Logical approach to the solution of problems that lend themselves to investigation. I mean, the scientific method is great. It's a great tool, not just for science, but for everything. You got a problem, you figure out what the problem is, you analyze it. Maybe you try this, you try that. This doesn't work, try something else. This does work, you got it, boom, solution. That's the scientific method. I mean, it is. Now, I could get a lot more specific, and I have here. So you identify a problem. I got to have that first. Observe and collect some data. Formulate a hypothesis. What do you think the relationship is between the data? Create a theory. Formulate a reasonable explanation based on the data. In other words, a theory, and chemistry is full of theories, so is physics. And a theory is just that. Based on the up-to-the-minute data, you can assume the theory is true. Until, of course, somebody comes along and proves otherwise. The atomic theory has undergone several revisions, multiple revisions, from its humble beginnings back in the Greek Roman days through now. And so it has undergone a lot of revisions, and each time it has, all we've done is just taken what we thought we knew and either expanded upon that or possibly even changed it entirely. But while a theory is in force, it's good. You can accept it as fact. But like I said, it's not set in stone. I made a note here. A law differs from a theory in that it only describes a natural phenomenon or a relationship between data, but it doesn't explain why. A theory explains. A theory is very explanatory. A law just states the relationship. We got a lot of laws in chemistry, and physics too. So, for instance, Charles' law. Charles' law in chemistry says that the volume of a gas in a flexible container is directly proportional to the Kelvin temperature of that gas. All right, that's it. States the relationship. It doesn't say why. Doesn't say how we know that. It doesn't explain further why we believe that to be true. It's just a simple statement. All right. Now, there's a theory to back that up, but the law itself is just a statement. Okay. All right. And then, of course, testing. Testing, its purpose is to establish a theory's validity and or to test a hypothesis. So we do a lot of testing. And, that's why labs where it's at in chemistry. Okay. So let's move on. Properties of matter. All right. So matter is anything that has mass and takes up space. All right. Taking up space we call a volume. Okay. Mass is a measure of the amount of matter in a substance, and again, the amount of space that matter takes up or occupies is called its volume. Properties of matter are characteristics that can be used to identify it. Right? So, used to identify it. So, there's several different ways that we explain or identify matter, and I'll get into those next. So first, we have extensive and intensive properties. Okay? An extensive property depends on the amount of matter that is present in a sample. All right? Example, volume, mass, amount of energy. All right? These three things are dependent upon how much matter you have. All right? So you've got a 1 kilogram ice cube and you got a 10 kilogram ice cube. All right? Well, the 10 kilogram ice cube has more mass, it takes up more volume, and it has more energy associated with it than the smaller sample does, than the smaller ice cube does. Those are extensive properties. All right? They depend on the amount of matter present. On the other hand, we have properties that are called intensive. Intensive properties do not depend on the amount of matter present. It makes no difference how much there is. Those properties remain the same. I always remember this. Intensive properties are independent of sample size. Intensive, independent of sample size. For example, let's take the ice cube. So you got a 1 kilogram ice cube, 10 kilogram ice cube. Both of those ice cubes melt at 0 degrees Celsius. All right? They both do, or 32 Fahrenheit. Of course, that is at standard conditions of pressure, that is. Those two ice cubes have the same density. They have the same electrical conductivity, no matter what level that may be. If we melt that ice and heat the water, that water will boil at the same temperature, 100 degrees Celsius or 212 Fahrenheit. These properties do not change regardless of the size of the sample. Those are intensive properties, right? Extensive versus intensive. Okay? Then we have physical and chemical properties, all right? So physical properties are those that can be observed or measured without changing the substance's identity. We talked about identity change in our labs earlier. Physical versus chemical change. So I got a whole slew of list here. Color, hardness, density, texture, smell, taste, blah, 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 blah. Solubility, which is, does it dissolve in water or not? State of matter, melting point, freezing point. These are all physical properties. Right? These are all readily observable or measurable, and we're not going to do anything chemically to the substance in taking those types of measurements. State of matter is one of those physical properties. Solid, liquid, gas. Of course, we also have plasma, which is the fourth state of matter, but we would that's only found in the far reaches, upper reaches of the atmosphere. We would never be dealing with that, and so although it does certainly exist, we will not have any use for studying it in this class. So we'll just stick with the three main ones: solid, liquid, gas. Solids, of course, have a definitive shape and volume. Right? Liquids have a definitive volume, but they have an indefinite shape. They take the shape of their container. So, if you have a gallon of milk, whether it's in a gallon container or whether it's in 2 half-gallon containers or 4 quart containers or in, 16 glasses full, it's still a gallon, right? It's still a gallon. Now, it takes the shape of the container it's in, but the volume has not changed. Gases have an indefinite volume and shape. They take the volume and shape of their container. One little note here, vapor. A lot of people kind of could misinterpret vapor versus gas. All right. So a gas, I guess the easiest way for me to say this is a gas is a gas normally. All right. At normal conditions of temperature and pressure, oxygen is a gas. Okay, it's a gas. On the other hand, at normal conditions of temperature and pressure, water is a liquid. But when we boil water and turn it into a gas, we don't call it water gas. We call it water vapor. Right? That's the difference. So a vapor is a substance that is in the gas phase that normally or naturally occurs as a solid or liquid. And it's either been heated or pressurized or both in order to be converted to a gas. Right? So a gas is a gas normally, and a vapor is a gas, something in the gas phase that normally would not be. Okay, that's the difference. Okay, next. Chemical properties. All right, so we have physical properties, now we have chemical properties. These describe the way a substance may change or react in order to form a new substance. So I got another list here, right? Flammability, chemical reactivity, blah, blah, blah. Those are all chemical properties, all right? Chemical properties. All right, now, changes in matter. So we have physical changes, we have chemical changes. We've discussed this before, or I know you've heard it before, even if it wasn't in here, it was somewhere else. So a physical change will alter a substance without changing its composition. The key to a physical change is that the identity is still the same. The substance's identity is still the same, hadn't changed a bit. So if you do any of these things to a substance, cut it into smaller pieces, grind it up into smaller particles, bend it, freeze it, melt it, boil it, etc., etc. Does it look different? Oh yeah, it looks different, but it's still the same stuff. All right, it's still the same stuff. Physical change. Chemical change is one in which one or more substances are converted into something different, something new. So a chemical change occurs during a chemical reaction. Burning, rusting, and we mentioned burning, I think. Burning, rusting, tarnishing, metabolism of food, those are all chemical changes. Right? Let me advance this real quick. So, real briefly on an equation, this is like way ahead of the game because we're going to just spend oodles of time on equations later on in this class. The starting substances in a chemical reaction are called the reactants. They are found to the left of the arrow. And the new substances that are formed are called the products. So reactants react together to produce the products. So reactants produce products. Okay? So here we have a little example here of that, where hydrogen and oxygen gases. Notice here, this equation is what we call a balanced equation. I'm sure you've seen that before. We'll get into that more later. The equation is balanced as it needs to be because of this right here, conservation of mass. And we've also listed here the states of matter of the substances. Maybe you've done that before, maybe you haven't. In here you will. Gas, and liquid, of course. Okay, let's talk about the conservation of mass. All right. So in in honors in activity 1-1A, we looked at that already. For those of you in Chem 2, we looked at that when you were in Chem 1. And we talked about it numerous times, and we will talk about it numerous times again in this class. Regardless of which class you're in, this is pretty much the same story. So, remember, the conservation of mass says that mass is not created nor destroyed during any type of change. All right. So whether it's a physical change to a substance or a chemical change involving a substance or multiple substances, the total mass of the system, both before and after the change, remains the same. All right? Remains the same. So, for the above example, in the chemical change involving the reaction of hydrogen and oxygen to form water, the question is, if 4 grams of hydrogen react completely with 32 grams of oxygen, then how many grams of water are you going to get? Well, based on the conservation of mass, if you start with 4 and 32, which is 36 grams of your reactants, then the products would equal that same 36 grams. So, simply put, 36 grams of water. The mass before the change and the mass after the change is equal. Okay. In the following physical change, if 125 grams of ice are melted, then how much liquid water are you going to get? Well, same amount, 125 grams. Mass before the change equals mass after. In the following chemical change, if 2.75 grams of iron are burned in air and 3.93 grams of iron 2 oxide are formed, then how much oxygen from the air did you use? Okay, well, this was similar to what we did in 1-1A, burning steel wool. You guys in Chem 2 remember that? Honors, we just did it not too long ago. We burned steel wool. Remember, that was the only reaction where the mass appeared to increase over the course of the reaction. You know, the steel wool measured a certain amount of grams, but when you measured the steel wool after you burned it, it weighed more. It's like, whoa, what happened there? Well, what happened was there was another reactant involved in that reaction, which of course was the oxygen gas out of the air. Got to have oxygen to burn anything. All right. And so basically then where we're at here is this 3.93 grams that we ended up with not only includes the 2.75 grams of iron, but it also includes the amount of oxygen in the air that was used. So if I subtract those two, excuse me, we get 1.18 grams of O2, of oxygen. All right, 1.18. Again, mass before a change, mass after a change, equal. Okay? Equal. All right. Types of matter now. We talked about changes in matter. We talked about classification of matter. Conservation of mass. Let's look at specific types of matter. So we have elements and compounds. The simplest form of matter is the element. It's a pure substance made of only one type of atom or one type of particle. We've kind of looked at that when we're doing particle diagrams. All right. Carbon atoms are unique to carbon, and they are not the same as oxygen atoms. All right. So they have a different. Their particle is different. All right. Right now there are 118 elements. All right. 118. A compound is a pure substance that can be separated into elements only by a chemical reaction or by chemical changes. All right. So let me advance that a little bit. So what I'm showing here Sugar, of course, is a compound. If this is common sugar, sucrose, C12H22O11. And you must heat or burn sugar in order to start the chemical reaction to separate it into its component. So when you do that, you get, it turns black. That's the carbon. And then it also gives off water, all right, water. Now, which is a compound. So sugar is a compound. Carbon, though, is an element. Water is still a compound. Now, to break water down into its elements, it has to undergo electrolysis. Boiling water doesn't change it to hydrogen oxygen. That just changes it to a gas, to a water vapor. But if you run an electric current through water, you will break it down or decompose it into hydrogen and oxygen gases. So these are chemical changes, all right? These are chemical changes. I mentioned that pure substance, or that compounds are pure substances. Well, elements and compounds both are pure substances. So let's look at that one. So a pure substance has a fixed composition, and every sample of that pure substance has the same exact properties. And a pure substance could either be an element or a compound, one of the two, all right? A mixture, on the other hand, is a physical blend of two or more pure substances, each of which retains its own identity and properties. All right, so if you take salt and sand and you throw them in the same container and stir them up, there's no chemical reaction. All right, it's just salt and sand. All right, it's still salt and sand. They still have their own identities. We could separate them if we needed to. Nothing's changed chemically about either one. Okay, so that's a mixture. There's two types of mixtures: homogeneous or homogeneous, however you prefer to say it. Its composition is uniform throughout, no matter what the sample size. All the components of the mixture are always in the same proportion in every sample. Solutions are homogeneous mixtures, as are alloys, like brass or stainless steel or something like that. Any solution where you take something and dissolve it in water or some other solvent is a homogeneous mixture. All right. So, if you make Kool-Aid, that's a solution. That's a homogeneous mixture. Whether you take a drink from the top or the middle or wherever in the Kool-Aid, or take a sample from anywhere in that Kool-Aid, if it's all dissolved, it's going to taste the same because the components of the mixture are uniformly distributed in every sample. Okay, that's homogeneous. A heterogeneous mixture, or heterogeneous, is not uniform throughout. Its composition can vary depending on the sample. All the components of the mixture may be there, or they may not, but not in the same proportion. Usually a heterogeneous mixture settles by density, all right? Settles by density. Soil. Soil's got, clay and pebbles and other types of dirt, twigs, bugs, whatever, leaves. And when you take multiple samples of soil, even from the same big pile of it, are you going to get all those things in the same proportion in every sample? No way. All right. Muddy water. Well, if you ever, took a sample of water, if you're fishing on the creek or river or whatever, and you put some water in a bucket for your fish, and scoop it out of the river and you sit it in the bucket, you'll notice after a while the upper portion of the water is cleared somewhat, and the bottom is where all the mud settled. Well, that's because the mud is more dense than the water, and so it is separated by density. Milk, concrete, Italian dressing, or some other examples there. All right. Milk has cream in it. That's what gives it its white color. If you pour a glass of milk and let it sit for a long time, the cream will go to the top and the water will sink beneath it. Okay? So, yeah. Heterogeneous. With milk, it takes a while, but it's still heterogeneous. Okay, so that's a quick look at some general terminology in relation to matter. I think now we're ready to get started, at least just a little bit, on measurement. We're gonna hit that hard tomorrow I just want to do a quick review. This should be review for everybody on exponential or scientific notation versus regular decimal format. Okay, so let me advance that. Okay, so the numbers in our numbering system, which is base 10, that are extremely large or small, can be written in shorter format. It uses a number between 1 and 10, along with a power or multiple of 10. This method is called scientific notation. Now, here's a number. I counted them right. 602 and 21 zeros. That's a rather large number. That is a number we use in chemistry a lot. It's called Avogadro's number. And I sure as heck don't write it like that because it's not real convenient. But I do write it all the time as 6.02 times 10 to the 23rd. All right, so numbers that are extremely large or extremely small, scientific notation is the way to go. And in fact, in most all your calculators, you can only go 9 digits or maybe a few more than that. But once you get beyond that, it's going to take you to scientific notation automatically. All right, otherwise our display screens on our calculators would be this wide. So anyway, here's the format. This is a number here between 1.00 and 9.99, or so greater than 1, greater than or equal to 1, but less than 10, times 10 to some power. That's the sum exponent. So to convert, so again, this here, Avogadro's number is an extremely large number. It's 6.02 times 10 to the 23rd, a positive 23. So for numbers whose values are greater than 1, you will end up with a positive exponent in scientific notation. All right, so for numbers that are greater than 0, but less than 1, all right? So numbers from 0, but less than 1. Decimal numbers, basically. You're going to be using a negative exponent. Okay? So, to convert a regular number to one in scientific notation, you're going to move the decimal in the number in such a way that you end up with a number between 1.00 and 9.99. The exponent value is equal to the number of places you move the decimal. Right? If you had to move the decimal to the left, which means it's a big number, the exponent will be positive. If you move it to the right, meaning it's a small number, decimal number, the exponent will be negative. So let's look at that real quick. So here we have, I'll put that up a little bit. There we go. So here we have 45,000. So of course there's no decimal here, but we know that it's there at the end of the last 0, even though we don't write it. The only way I can move this decimal and get this number down to a number between 1 and 10 is to the left. So if I go 1, 2, 3, 4 spots, that gets me to 4.5, which is between 1 and 10. That's where you know when to quit. All right. So this is 4.5 times 10. We moved it 1, 2, 3, 4 places to the left, so it's positive 4. So 45,000 is equivalent to 4.5 times 10 to the 4th. Next one, so we do have a decimal point. This is a very small number, so it's going to have a negative exponent, as we just said. So to get this number to a number between 1 and 10, I'm going to have to move the decimal to the right, 6 places actually. That puts it between the 6 and the 7, so 6.7 is between 1 and 10. 6.7 times 10, I moved it 6 places, negative 6. Okay? To convert a number in scientific to a regular number. All right, so now we're going to do the opposite. The exponent value is equal to the number of places you move the decimal. All right? Let me raise this up. If the exponent is positive, then you move the decimal to the right. All right, so now we just flipped it around. Everything's backwards. All right. If the exponent is positive, you move the decimal to the right, meaning you're making the number bigger, because positive exponent numbers are big numbers. Right? If the exponent is negative, we're going to move the decimal to the left, which is going to make that number smaller, which is exactly as it should be. So here we have 8.20 times 10 to the fifth. All right. Well, 5 means we're going to move it 5 places. Positive 5 means we're going to move it 5 places to the right. All right. So positive exponent, move the decimal to the right. So we have 1, 2, 3, 4, 5. All right. So we're going to start off with 820. But now you see we have 1, 2, 3 empty, whatever you want to call it, empty humps. All right. And what do you fill in there? Well, you fill in there with zeros. So we got 1, 2, 3. Put a comma in there for standard, whole number writing, and it's 820,000. Okay. Next one, 7.36 times 10 to the minus 7. The 7 means that we're going to move the decimal 7 places. The negative sign means we're going to move it 7 places to the left. All right, so we're going to make this number smaller, as we should. So here's the decimal now. So we have 1. Now we got 6 more to go. 1, 2, 3, 4, 5, 6. Now there's the decimal. All these fill in with zeros. All right. So it'd be, let's see if I count. 1, 2, 3, 4, 5, 6. So decimal point 0, 0, 0, 0, 0, 7, 3, 6. And of course, you could put another 0 there. That's perfectly fine. You don't have to. Either one of those reads the exact same way. Okay. So there you have it. There you have it. That is where I'm going to stop today's lesson. So refer back to our schedule. You both have, now honors you guys have to do 1-1B, which is some more practice with rounding and recording. But both classes have a measurements review assignment that you are to start on for tomorrow. In both cases, you are to do problems 1, 2, and 3 only. Make sure you look at the directions carefully and just complete those 3. And then we are going to start with metric conversions and significant figures tomorrow. So until then, this is Mr. Keister signing off. Everybody take care, stay safe, and I will see you again soon. So long, everybody.